In a secret facility deep in the Chinese countryside, engineers stood before the wreckage of an American F-4 Phantom fighter jet, their mission seemingly simple: reverse engineer one of the most formidable combat aircraft ever built. What followed was a tale of ambition, espionage, technological hubris, and ultimate failure that would expose the vast gap between copying a design and understanding the science that made it deadly. The prize. The story begins on a humid morning in April 1965 when an American F-4 Phantom conducting reconnaissance over North Vietnam was struck by anti-aircraft fire. The pilot managed to nurse the damaged aircraft toward the relative safety of the Gulf of Tonkin, but the damage was too severe. Both crew members ejected successfully and were recovered by rescue helicopters. But the aircraft itself plunged into the shallow waters near the coast, waters that, unknown to American intelligence at the time, fell within an area patrolled by Chinese naval vessels. Within hours, Chinese salvage teams were working to recover the wreckage. The operation was conducted with remarkable speed and secrecy, with the aircraft's major components, including engines, avionics, and structural elements, pulled from the water and transported to a classified facility in Shenyang, one of China's primary centers for aircraft development. For Chinese military planners, this was an unprecedented opportunity. The F-4 Phantom represented the cutting edge of Western military aviation technology, and possessing an actual example, even a damaged one, was an intelligence coup of extraordinary value. Colonel Zhang Wei, the chief engineer assigned to lead the reverse engineering effort, first laid eyes on the salvaged components in May 1965. What he saw was both exciting and daunting. The Phantom was a technological marvel, a massive twin-engine fighter capable of speeds exceeding Mach 2, armed with sophisticated radar and weapon systems, and built with materials and manufacturing techniques that were, in many cases, completely unfamiliar to Chinese engineers. Zhang was no novice. He had been educated in the Soviet Union during the 1950s, had worked on China's early jet fighter programs, and understood both the potential and limitations of Chinese aerospace capabilities. But as he examined the Phantom's remains spread across the facility floor, he realized the magnitude of the challenge before him. This wasn't simply a matter of measuring dimensions and copying shapes. Every component represented decades of American research, industrial expertise, and manufacturing capabilities that China did not possess. The Chinese leadership, however, was insistent. Chairman Mao's vision of China as a global power required military capabilities that could challenge American dominance in the Asia-Pacific region. The F-4 Phantom, which was proving devastatingly effective in Vietnam, represented exactly the kind of capability China needed. The order came down from the highest levels: study the aircraft, understand its technology, and produce a Chinese equivalent that could match or exceed its performance. Zhang assembled a team of China's best aerospace engineers, metallurgists, electronic specialists, and manufacturing experts. They were given virtually unlimited resources, at least by Chinese standards, and told that failure was not acceptable. What followed was a 3-year intensive effort that would ultimately expose fundamental weaknesses in China's technological and industrial base. The complexity of modern warfare. The F-4 Phantom II, designed by McDonnell Aircraft Corporation in the late 1950s, was the product of an aerospace industry that had been perfecting jet fighter technology for nearly 2 decades. Every aspect of its design reflected accumulated knowledge, sophisticated engineering, and manufacturing capabilities that represented the pinnacle of American industrial might. The airframe itself was constructed primarily from aluminum alloys, but not just any aluminum. American engineers had developed specific alloys optimized for strength, weight, and resistance to fatigue, the repeated stress that aircraft structures endured during combat operations. These alloys were produced using carefully controlled metallurgical processes, with precise combinations of elements and heat treatments that gave them properties superior to standard materials. Zhang's metallurgy team spent months analyzing samples from the Phantom's airframe, trying to determine exact compositions and manufacturing processes. They could identify the basic elements, aluminum, copper, magnesium, zinc, but determining the precise proportions and understanding the heat treatment processes proved maddeningly difficult. Without this knowledge, any airframe they built would be heavier, weaker, or more prone to failure than the original. The engines presented an even more formidable challenge. The F-4 was powered by two General Electric J79 turbojet engines, each capable of producing over 17,000 pounds of thrust with afterburner. The J79 represented 15 years of continuous development in jet engine technology, incorporating advanced features like variable stator vanes, sophisticated fuel control systems, and turbine blades manufactured from exotic materials capable of withstanding temperatures that would melt ordinary steel. Dr. Liu Chen, Zhang's lead propulsion engineer, examined the salvaged J79 engines with a mixture of admiration and despair. "These engines are works of art," he told Zhang during one of their weekly progress meetings. "The turbine blades alone, they're single crystal castings with internal cooling passages. We don't have the capability to manufacture anything like this. Our best turbine blades are forged from conventional alloys and can't withstand even half the operating temperatures these achieve." "Can we develop the capability?" Zhang asked, though he already suspected the answer. Liu shook his head slowly. "Possibly, but it would take years, perhaps a decade or more. We'd need to develop entirely new metallurgical processes, build new manufacturing equipment, train specialists who don't currently exist in China. And that's just for the turbine blades. The entire engine is filled with similar challenges." The avionics and weapon systems presented yet another layer of complexity. The F-4's AN/APQ-120 radar was a sophisticated pulse Doppler system capable of detecting and tracking multiple targets simultaneously, even in the presence of ground clutter that would blind simpler radars. It incorporated technologies, traveling wave tubes, solid-state components, and signal processing techniques that were at the frontier of electronics in the mid-1960s. Zhang's electronics team, led by a brilliant young engineer named Dr. Wang Mei, made some progress in understanding the radar's basic operating principles, but actually replicating it proved impossible. China's electronics industry in 1965 was decades behind the United States in terms of component miniaturization, reliability, and sophistication. The vacuum tubes and transistors available to Chinese engineers were larger, less reliable, and less capable than their American equivalents. "We can build a radar," Wang reported to Zhang after months of effort, "but it won't be this radar. We can probably achieve perhaps 30 to 40% of its performance, and it will be twice as heavy and consume 3 times as much power. For a real equivalent, we'd need to leapfrog an entire generation of electronics technology." As the months stretched into years, Zhang found himself confronting an uncomfortable truth. Reverse engineering the F-4 Phantom was not simply a matter of copying what they saw. Every system, every component, every material choice in the aircraft represented the end product of vast technological infrastructure. Research institutions, specialized manufacturing facilities, supply chains, and accumulated expertise that simply didn't exist in China. The prototype that never flew. Despite the mounting evidence that a true F-4 equivalent was beyond China's capabilities, political pressure demanded that something be produced. Zhang and his team made the difficult decision to create what they internally called a functional demonstration, an aircraft that borrowed some design elements from the F-4 but used technologies and materials available to Chinese industry. The result, designated J-8 in official documents, though it bore little resemblance to what Zhang had originally envisioned, was a compromise in every sense. It retained the Phantom's basic twin-engine configuration and general layout, but almost everything else was different. The engines were Chinese-built copies of Soviet designs, producing roughly half the thrust of the J-79s.
The airframe was constructed from Chinese aluminum alloys that added significant weight. The avionics were simplified to the point where the aircraft's combat capabilities were severely limited. Construction of the first prototype began in 1967, but progress was repeatedly disrupted by the chaos of the Cultural Revolution. Engineers were denounced as bourgeois intellectuals, facilities were ransacked by Red Guards, and critical technical documentation was destroyed as suspected Western influence. Zhang himself spent 3 months in detention, subjected to criticism sessions where he was forced to confess imaginary crimes against revolutionary purity.
When order was finally restored and work resumed in 1968, the team discovered that much of what they had accomplished had been lost or damaged. They essentially had to start over, this time with even fewer resources as China's economy struggled under the weight of political upheaval. The first prototype was finally completed in July 1969, more than 4 years after the project began. It sat on the tarmac of the Shenyang test facility, looking superficially like an F-4 Phantom, but betraying its compromises to anyone who looked closely. It was heavier, less refined in its construction, and lacked many of the systems that made the Phantom such a formidable combat aircraft. The first flight was scheduled for August 15, 1969, with China's most experienced test pilot, Major Chen Guohua, at the controls. Zhang watched from the control tower as Chen taxied the aircraft to the runway, his emotions a mixture of pride in what his team had accomplished and anxiety about what was about to be tested. The takeoff roll seemed longer than it should have been, a consequence of the aircraft's excess weight and underpowered engines. But Chen managed to get airborne, climbing slowly into the overcast sky. For 15 minutes, everything seemed to be going reasonably well. Chen reported normal handling characteristics, though he noted the aircraft felt heavy and sluggish compared to the Soviet-built fighters he had experience with. Then disaster struck. At approximately 8,000 feet, Chen reported a fire warning in the left engine. Standard procedure called for shutting down the affected engine and returning to base, which Chen initiated immediately. But as he throttled back the left engine, the aircraft began to behave erratically. The fire, instead of being contained, had apparently spread, damaging hydraulic lines that controlled the aircraft's flight surfaces. "I'm losing control," Chen's voice crackled over the radio, professional but tense. "Hydraulic pressure dropping. The aircraft is not responding normally to inputs." Zhang gripped the railing of the control tower, watching helplessly as the prototype began to descend in an increasingly unstable manner. Chen fought with the controls, trying to maintain enough stability to reach the runway, but the aircraft was quickly becoming unflyable. "Eject! Eject!" the tower controller ordered, but Chen was already ahead of him. The canopy blew clear, and a moment later, the ejection seat rocketed Chen clear of the doomed aircraft. His parachute deployed, and he drifted safely to ground, while the prototype, representing 4 years of intensive effort and China's ambitions to match American air power, augured into a field 2 miles short of the runway and exploded in a ball of flame. Chen survived with only minor injuries, but the prototype was a total loss. More significantly, the investigation into the crash revealed systemic problems with the aircraft's design and construction. The fire had started due to a fuel leak caused by inadequate sealing in the engine bay, a consequence of Chinese manufacturing tolerances that weren't as precise as those in American factories. The hydraulic system failure resulted from lines that were routed too close to hot engine components, a design flaw that reflected the team's incomplete understanding of the thermal environment inside a high-performance fighter aircraft. Reckoning with reality. In the aftermath of the crash, Zhang was summoned to Beijing to brief senior leadership on the project's status. He knew this meeting would be difficult. Chinese political culture did not easily accept failure, and there would be intense pressure to explain what had gone wrong and, more importantly, to promise that it could be fixed. The meeting took place in a conference room in the Ministry of Defense, with a dozen senior officials and military officers in attendance. Zhang presented his findings honestly, explaining the technical challenges his team had faced and the fundamental limitations of China's industrial and technological base. The F-4 Phantom represents approximately 20 years of continuous American development in aerospace technology, Zhang explained, using charts and diagrams to illustrate his points. It is not simply an aircraft that can be copied from examination of physical examples. Every component, every system, depends on manufacturing capabilities, material science knowledge, and engineering expertise that we do not currently possess. "Are you saying we cannot build such an aircraft?" one of the officials demanded, his tone suggesting that this answer would be politically unacceptable. "I am saying that we cannot build such an aircraft now using our current capabilities," Zhang replied carefully. "To create a true equivalent, we would need to invest decades in developing our aerospace industry, our metallurgy, our electronics manufacturing, and our overall technical expertise. There are no shortcuts. The Americans didn't develop the F-4 overnight. They built it on a foundation of continuous progress dating back to the earliest days of jet aviation." The meeting ended without clear resolution, but Zhang could sense the shifting sentiment in the room. The officials were beginning to understand what he had been trying to tell them, that technological superiority couldn't be stolen or copied, but had to be earned through long-term investment in education, research, and industrial development. The J-8 project continued in modified form, but with more realistic objectives. Rather than attempting to match the F-4's capabilities, the focus shifted to creating an improved version of existing Chinese fighter designs, incorporating whatever lessons could be learned from the Phantom without trying to replicate technologies that were beyond China's reach. A second prototype flew in 1970, this time successfully, though it was a much more modest aircraft than originally envisioned. It eventually entered service in limited numbers, serving primarily as an interceptor with capabilities roughly comparable to American fighters from the 1950s rather than the cutting-edge F-4. For Zhang and his team, the experience was sobering but ultimately educational. They had learned valuable lessons about their own capabilities and limitations, lessons that would inform Chinese aerospace development for decades to come. More importantly, they had learned that real technological advancement required patient, systematic development of fundamental capabilities rather than attempting to leapfrog ahead through reverse engineering alone. The long game. The failed attempt to copy the F-4 Phantom became, in retrospect, an important turning point in Chinese military-industrial development. Rather than continuing to focus exclusively on reverse engineering captured or purchased foreign technology, Chinese leadership began to invest more heavily in fundamental research, engineering education, and industrial infrastructure. This shift didn't happen overnight, and China continued to study and learn from foreign technology whenever possible. But there was a new understanding that real capability required building a domestic base of expertise and manufacturing prowess that couldn't be shortcut through copying alone. Zhang continued to work in Chinese aerospace for another 20 years, eventually rising to senior leadership positions in the industry. In his later years, he occasionally gave lectures at engineering universities, using the F-4 project as a case study in the importance of understanding not just what to build, but how to build it and why it works. "When we first saw that F-4, he would tell students, we thought we were looking at an airplane, but we were actually looking at the entire American aerospace industry, the research institutions, the manufacturing expertise, the supply chains, the accumulated knowledge of thousands of engineers and scientists. You can't copy that by measuring dimensions and taking photographs. You have to build it step by step through years of dedicated effort." By the 21st century, China had indeed built that capability. The Chinese aerospace industry produces sophisticated fighter aircraft, commercial airliners, and space vehicles that incorporate indigenous technology, and in some cases rival or exceed the capabilities of Western equivalents. But this achievement came through exactly the patient, systematic development that Zhang and his team's failure had pointed toward, not through shortcuts or copying, but through genuine technological advancement. The F-4 Phantom itself remained in service with various air forces around the world for decades, eventually becoming a symbol of 1960s American military technology. China never did successfully copy it, but the attempt and the failure taught lessons that proved more valuable in the long run than any short-term success might have been. Zhang Wei retired in 1990 and passed away in 2003, but his legacy lives on in the Chinese aerospace industry he helped to build. The young engineers who once stood bewildered before the wreckage of an American fighter became the senior leaders who guided China's eventual emergence as a major aerospace power. They never forgot the lessons learned from their failed attempt to copy the F-4 Phantom, and those lessons shaped their approach to technology development for generations. In a final irony, modern Chinese fighter aircraft like the J-20 bear no resemblance to the F-4 Phantom, representing instead indigenous design philosophies developed through decades of Chinese research and development. The dream of copying American technology gave way to something more substantial: the capability to create Chinese technology that stands on its own merits. And that achievement, born from failure and humility, represents a far greater success than any copy could have been.